Good afternoon. Thank you, everyone, for being here. Um, let me start. So this talk is going to be about how to construct and build real world crypto systems. More specifically, how to build a secure channel. My pointer is working. That's great as well. Okay. So just a very brief overview of the things that we are going to discuss. So I would like to start off with some fun crypto theory, like what are these secure links, if you will. More specifically, we're going to discuss some security notions, and then we're going to dive into trying to make such a secure link, if you will. We're going to discuss how can we design such a protocol which builds a secure link. We're going to look at TLS 1.3 and SSH v2 to see how they try to build a system, and then we're going to conclude. Okay. So some fun theory to start with. Okay. So what is this secure link that we are trying to build, right? So conceptually, this is a channel which we're going to use to send over different messages, and we want those messages to have very specific properties. More specifically, we want to guarantee that what we send over this link is, first of all, confidential, right? That no one can read what we are sending, that's one. We want to make sure that the data that we are sending over this link has not been modified, which we're going to denote by this integrity notion. And we're going to assume that the network that we're going to use to send over this data is untrusted, right? So this conceptual goal is done, is created, if you will, by something that we call a secure channel. So there has been in the past a lot of research done about this notion, and more specifically, those two people here has defined a secure channel as a channel protocol that both provides secure authentication, if you will, and secure encryption, meaning that we are going to authenticate the two parties which are talking to each other. That's one, and secondly, we want to make sure that the data that we are sending over this specific channel implementing this secure encryption protocol also provides encryption, so that no one who is not allowed to see the information being exchanged cannot read it, right? And very often you will see that this construction, this channel is done via messages. As in, we have two parties, party A and party B, and they will both exchange messages. So what is the goal of this channel, if you will? So as I said earlier, we want the data which is being exchanged over this link, over this channel, has confidentiality, right? We want to make sure that the data being exchanged over that link is kept secret. That no one who is not allowed to see it, to read it, can actually read it. That's one. We want to make sure that the data being exchanged over this link has the property of integrity, meaning that if the data is exchanged, we want to make sure that it cannot be modified. Or if it is being modified, that we can see that we can detect that okay, the data is changed while it was being transferred from point A to point B. Then the third property that we want is we want to have data authenticity, meaning that the origin of the data, as in party A or party B, we want to make sure that there is some sort of a known entity bound to the site which is sending the data. That's the third requirement, data authenticity. So those three properties are from a security point of view. What else would we like to have for this specific secure channel is the following two properties. We would like to have that any type of application can use this secure channel. So we would like to have this secure channel to facilitate protocol multiplexing, as in the higher level protocol should be every type of protocol, if you will. And a second requirement, if you will, would be that when something goes wrong on this secure link, that information can be translated or communicated to the link, not to the link, to the layer above it. So, for example, if there is some sort of a man in the middle, and he or she tries to tamper with that information, tamper with the data being exchanged, that notion, that fact should be able to be communicated to the layer above. Okay, so to create some context or to just set up this secure channel, we will have three persons, if you will. We will have Alice, which you can see here. We will have Bob, and we're going to have Eve. So Alice and Bob are the two parties who will exchange information with each other, and you will have Eve, and Eve in this context will be our adversary who is trying to modify data over this channel. So you can see here this blue rectangle that will be labeled our channel, and the properties that we would like to have of this channel are the following: confidentiality, meaning data secrecy. So this M being sent by Alice to Bob can only be read by Bob, not by Eve. In integrity, you would like to make sure that this data is not changed while transferring. So if Eve would try to flip a bit in this M0, Bob would be able to see that and detect that as the second property. And then, excuse me, authenticity, we would like to make sure that the origin is bound to a known entity, meaning that M0 being received by Bob here, Bob knows that M0 has been sent by Alice. Those are the three main requirements of our channel, of our secure channel. Okay, so how does that look in terms of a stack? So we have again here Bob and Alice. We're going to have this application layer, as you know, for example, with the OSI stack. We will have the application layer, and then below that we will have this secure channel. So, and it is required of the secure channel or of typical channel implementations that they can be reused with different application layers. Meaning that this secure channel should be able to handle multiplexing of different data. Okay. So with that, we have these three properties of our secure channel, namely data confidentiality, data authentication or data authenticity, and data integrity. And I would like to take the time now to actually discuss those three specific properties in a bit more detail. So if we say secure, for example, we look at confidentiality and we say this specific scheme or construction provides data confidentiality. What exactly does that mean? So I would like to spend the next few slides looking at that from a more formal perspective. So what we are going to do is we are going to play some sort of a mind game, if you will. Some sort of a game where we are going to try to understand what confidentiality means exactly. Confidentiality, data authentication and data authenticity, and data integrity. Okay. So to set up in our very simple game or our very simple model, we're going to have Alice, which you can see here. We're going to have Bob, which you can see here. We have this channel, which Alice and Bob can exchange messages on. And then we're going to say that they have performed a key exchange, as in they both have knowledge of a key K. So Alice knows key K and Bob knows key K. And this has been done out of band of the normal channel. So Eve does not know key K. So Alice and Bob, two parties which will exchange messages, and Eve, which will be our adversary in this context. So let's go over a bit more formal notation. So we have the channel, we have our encryption function E, which will be done over, which will be use key K shared between Alice and Bob. And they will take the plain text message, as in the normal readable message. And under this transformation, Alice will create C0. Okay, and then on the other side, Bob, which also has knowledge of key K, can take this ciphertext being exchanged over the channel and can decrypt it using his key K, getting back the original message. Same thing here, Bob can use, can create message M0, can use the encryption function here to create C1, and he can send that to Alice, and Alice can decrypt that message. So E encryption using key K of message M0 produces ciphertext C0. So that is what this notation means. Okay, so let's now look at what we mean. What does it mean if we say that something provides confidentiality? And what does confidentiality mean exactly? So we are going to play a small game, if you will. So we have Alice here and Bob here, and we have Eve here. What is Eve going to do? Eve is going to submit messages M0 and M1 to Alice and Bob. She can choose those messages. Eve chooses those plain text messages. What is Eve going to do? Is Eve is going to sample a bit B from set 1 or 2. She's going to sample that randomly. So she will choose a bit 1 or 0. And then Eve will take those two messages sent by Eve here, and she will encrypt MB, where B is the bit being sampled randomly from the set. And she will produce ciphertext CB. Now Eve will, Alice will transmit this message to Bob, CB, right? And Bob, obviously, having knowledge of key K, because they performed the key exchange before, is able to decrypt the CB to get back the original message, MB. Yeah? Now, because Eve also sent M0 and M1 to Bob, Bob is able to guess this bit B with a chance of 1, because he has a copy of the messages transferred, and he has a copy of the shared key K. So Bob is able to decrypt that specific message and get back the original message. Okay. Now Eve, or adversary here, will also read the ciphertext, and now her task is to guess the value of bit B. Is it 0 or 1, which is the bit sampled here. Now, if Eve is not able to distinguish encryptions of M0 of M1, meaning that the chance of her guessing the value of B is 1/2, we say that this construction E provides confidentiality. Eve is not able to distinguish between encryptions of M1 and M0. That is formally how we define confidentiality in this very simple model. So let's go a step further. Let's extend on this existing model. And what does confidentiality mean when we are reusing the key? Meaning that we are going to encrypt more than one message. Okay, let's go over this step by step together. So we have here again the same setup. We have Alice, and we have Bob on the other side, the two parties which will exchange messages. And we have Eve here in the middle. Eve is going to firstly submit two messages, just like we had with the previous model. Yeah. So she's going to submit M00 and M01. Alice, receiving this information, she will encrypt message M0B, right, where the B is again the bit being sampled randomly from the set here. And she will encrypt C0B. And she will send that information towards Bob. Now again, just like with the previous model, Bob will be able to decrypt this message. Why? Because he has a copy of the key K, right? So he will be able to get back this bit B here. Now Eve, obviously, is able to get that ciphertext C0B, and her task is still to guess bit B. What is this bit B? Is it 0 or is it 1? Now, the difference with the previous model is Eve is now allowed to send the second pair of messages, which you can see here. She is allowed to send M01 and M11. Right? And now Alice will indeed encrypt message M0B, where the B's are the same. And she again will send the ciphertext over to Bob, which Bob can obviously decrypt because he has the shared key K. Now the task of Eve is again to guess this bit B. So imagine now the following, where in the previous slide we had only one pair of messages, M01. We now have two pair of messages. So imagine now the following, that M00 and M01 are the same. They are the same message. Right? And M01, apologies, M10 is the same as M00. And M11 is just something else completely. Now Eve will be able to guess bit B with a chance of 1, because if M00 and M01 are the same, she will get the encryption of M of the same message. This will be the same as this. This will be different. So she can now perfectly distinguish between encryptions of M00, M01, or M10 or M11. So something, a construction, or apologies, an encryption function, which will be secure in this model, will no longer be secure in this model. So if your encryption is deterministic, that specific scheme or construction will fail here. And obviously Bob is able to always get bit B. Why? Because he had a copy of the key. So that is how we formally model confidentiality. Okay, so authentication or authenticity. So we're going to make our model a bit more difficult. So we're going to have now this rock here, which will be an oracle, which is able to perform arbitrary decryptions. So again, Eve will submit message M0 and M1 to Alice. Alice again has this bit B. She will send over that encrypted message, CB if you will. Bob can decrypt it because he has key K. And now here we have that Eve is allowed to get decryptions of arbitrary ciphertext. The only restriction which we have in this model will be that whatever Eve submits to the rock, the oracle if you will, have to be different that from what is being sent from Alice to Bob. Right? So what do we need in order to get to this, to get something secure in this model? Will be we need to somehow be able to authenticate our message. The rock here should be able to distinguish between ciphertexts which are valid or invalid. That is how we model authenticate encryption typically. So now the last property of our channel, integrity, data integrity. How do we formally model that? So imagine now that we have again Alice, Bob, and Eve. Alice will encrypt message M0 to C0. She will transfer that. Eve is able to capture that. Eve has again access to this oracle, meaning that she can get arbitrary decryptions of ciphertexts, which are different from the one being exchanged. And now the objective of Eve is to make a ciphertext which is still valid, which is valid for Bob to decrypt. So we see here Alice sends the C0. Bob can obviously decrypt it because he has the shared key K. Now Bob is going to encrypt message M1 to C1. But now here Eve is going to submit her ciphertext, if you will, towards Alice. And the question that Alice now has to answer is M star something that Bob wrote? How is she able to know that whatever she is decrypting is indeed something coming from Bob? Like, how does she know that the ciphertext is valid? If we have a construction which provides for integrity, then that means that the question asked by Alice is something that we can answer. That is what we mean by integrity in this specific model. And just to remind you that these are all properties which should come from our secure channel. Our secure channel should provide for these basic properties. So now the final property that I would like to show you is stateful exchange of messages. For example, imagine the following. We have again Alice and Bob here. Alice is going to encrypt message M0 to C0 and exchange it to Bob. Bob is going to encrypt two messages, M0 and M2, apologies, M1 and M2 to C1, C2. And imagine now that Eve is able to exchange the order of data being sent from Bob to Alice. How does Alice know the order of the messages? Like very often in our OZ stack, we have our transport layer, TCP, for example, which will ensure the order of the data being exchanged. One level higher, that might not be the case. How can that one level higher, our secure channel, make sure that the other side is able to get the order of the messages being exchanged? That's something else that our secure link should also provide for. Being able to be able to ensure the order of the data being transferred. That is what we call a stateful secure channel. We are able to distinguish, we're able to get the order of the messages being exchanged. So with that, we are past by the more formal and more theoretical stuff. Let's now discuss on how we can actually construct such a secure channel. If we are building applications, we're building systems, and we would like to have these specific properties, we need to build a secure channel. How can we now do that? It's a good question. So let's go over the different phases, if you will, of such a secure channel. So first of all, what we need is we need somehow a way to exchange keys. So the first thing that we need is something which we will refer to as the key establishment protocol. We have one, two, or multiple parties which should be able to agree on a key used for encryption, for a MAC, for authentication codes, for whatever. Okay, and depending on the exact setting, we would like to have one, two, or multiple parties to be authenticated to every other party. Okay, so we need to have some sort of a authenticated key establishment protocol. This is very often done by using asymmetric or symmetric cryptography. Then for phase two, we need somehow to have a way to, from that key establishment protocol, to derive more keys, because we will need more than one shared secret to build this secure channel. So we'll need to have some sort of a key derivation phase where we can extract keys from, secondly, and then obviously a third phase will be we need to have some sort of a system construction in place to actually encrypt and secure the data being transferred over each other. So again, encryption will provide us confidentiality, and then somehow we need to have authentication, data authenticity, which will be done by a MAC, for example. So we need to have data authenticity and data origin authentication, which if we are using a authenticated key exchange will often be the case. Now, the slide I showed you previously, that was from a security point of view. Obviously, we need to have more than that to have a secure channel. So it would be nice if we could have a clean and well-defined API, because more often the people who are using a secure channel do not care about cryptography or difficult things like that. So they would like to have a fixed set of APIs that they can use without tweaking the exact configuration of our secure channels. So developer would like to have something as open, close, send and receive. So they would like to have some sort of a channel which they can call open on, which will construct a channel, which they can close again, which they can send data, and which they can receive data. Just like TCP, they would like to have a secure replacement for TCP. Something simple like that. Another question, is the channel stream-based? Is this the case with SSH, or is the channel based on messages being, one message being sent to another party, being back sent to another party? A third question is the errors on the secure channel. For example, we have an adversary which flips some bits, which will result in an error on the secure channel. How is that error translated to the application layer? Like, how does the application layer know that something went wrong on the lower layers? So we need to have a way of doing that somehow. So, apologies, I need this button. Does the channel the retransmission of data? Is that handled by the transport layer? Is that handled by the application layer? So somehow the question needs to be answered, which is important for our secure channels. Does the channel provide compression? Yes or no? These are all engineering questions that should be answered while you are designing and building your secure channel. And all these questions or features or properties listed here do have impact on the security of your link or of your channel. So these are important questions that should be asked. So let us now look on how we can design such a protocol. Like, this all sounds nice. How can we now make something like this? So again, what are the different phases, more concretely, of this secure channel, of the secure link, if you will? So we're going to, first of all, need to establish this channel between two parties, between A and B. How can we establish the notion of a channel? That's important. We will have to perform some sort of a key establishment so that both of them have a shared key that they can use to further have a shared key so that they can both derive new keys and other keys used to facilitate a secure channel. We need to obviously be able to handle the bulk transaction of that channel, as in somebody is uploading a file to somewhere. That would be a large set of data. That data needs to be exchanged to the other side, obviously. So we need to be able to handle secure data transfers. And then when everything is finished, we need to close down this protocol and finish this protocol. Those are, if you will, the four big phases of a secure channel protocol run. Let us now take a step back and abstract this a bit. So part one, we're going to perform an authenticated key exchange. This can be done typically using two techniques. So the first one will be key creation, as in Diffie-Hellman. I assume that most of you know what the Diffie-Hellman key exchange is. That's one way of doing it. Both parties will provide some information used to create the key. Diffie-Hellman, both parties provide data, and then both parties are able to derive the key from the exchange data. That's one way, using Diffie-Hellman. Then we have key transport, typically using RSA. For example, in the context of TLS, you will have the client which will create a secret. The secret will be encrypted using the other side's public key, and then that public key, that encryption will be sent to the other side, and the other side is able to decrypt that message using its private key. So the difference here is that both parties will exchange data from which they can derive the key from. While using RSA, you have one party which will make a secret, encrypt it using the other party's key, using its public key. Then the other party is able to derive the private key, using the derived key, able to decrypt that message again. Oh, that's part one, key exchanges, and very often, or not very often, always in this Diffie-Hellman exchange or key using RSA, if it is authenticated, then the exchange also has to be authenticated. And then we have part two, which will be exchanging the data from party A to party B, using very often symmetric constructions, AES, things like that. Okay, so let's first have a look at the key exchange protocol. Oh. So authenticated key exchanges, called like this, is a protocol that specifies how two parties can create a shared key, which can then be used during the existence of that session. During the execution of the key exchange, it is desired, it is very often required, that linked to that is somehow authentication of the entities. So somehow we want to be able to have some assurance about the identity of the parties exchanging the keys, which is in the context of TLS often the case that the server has a certificate which will provide some information about the key used by that server, and that information has been certified by a CA, for example. So very often, somehow in the key exchange, we'll have some sort of a notion of authentication of the entities which are exchanging, which are performing this key exchange. So you cannot, well, it's not, very often you cannot see the key exchange different from the authentication of the entities. Very often those two things are combined. As you can see here, key exchange should typically be linked somehow to authentication. And obviously, as most of you know, we would like to have that the keys which are derived from this key exchange have this feature, this property of perfect forward secrecy. Now, what is perfect forward secrecy? Because I know that everybody knows the term here, but sometimes it's a bit confusing, like what exactly does that mean? So let me just explain briefly what perfect forward secrecy is. So we require that the AK provided keys are perfectly secure in the future. So you have here this small timeline. You have your the creation of your secure session here, and the secure session is finalized here. Here we will create some keys, and those keys will be used during this secure session to encrypt messages. The security guarantees of this key, namely providing confidentiality, needs to hold true even when the secure session is finished. So when a key is compromised, we want the guarantees of this AKE-derived key to still hold true. That's what we want. We want the key to be perfectly secure forward in time. So how are we going to do this concretely? We're going to introduce the notion of a long-term key, LTK, and a short-term key. So, for example, imagine Diffie-Hellman. We're going to perform a Diffie-Hellman key exchange. The specific values required to compute this Diffie-Hellman key will be created on the fly. And we are then, so this is the short-term key. We're going to build it right now. And then we're going to authenticate that key exchange by signing, for example, the parameters, the specific values used for the creation of the short-term key with this long-term key. So we have this exchange going from party A to party B, from party B to party A. And we're going to sign that somehow with keys which are part of, for example, the TLS certificate. So we're going to sign the exchange of Diffie-Hellman with our long-term key, which has been signed by a CA. So the key used to encrypt data during transfer, this short-term key, yeah, the messages used to exchange that will be signed by the long-term key. So the long-term key does not contribute to the key derived from this key exchange. And if we have that, we have perfect forward secrecy. Because the data used to create this key will be completely independent of the long-term key. So if the long-term key gets compromised, because the long-term key did not contribute to the creation of this session key, it doesn't matter if this key gets compromised, because it was not used to create this short-term key. So more formally, we say that AKA provides perfect forward secrecy if the disclosure of the long-term key does not compromise the derived session key. Okay. So now for the next phase, phase 2, if you will. We're going to quickly use at how we can derive more keys from this key exchange. So our AKA, or authenticated key exchange, will result in a shared secret, but we need more than one secret in order to build this secure channel. Very often we need more than one key. So typically what we will need is we have two parties, A and B, and both need to have a key to encrypt. So one party will have a read and a write key, the other party will have a read and a write key. Very often we need message authentication, so there will be a key for that. So we need more than one key. So in the context of TLS 1.3, the new specification, what they use is they use something called HKDF, which is an HMAC-based key derivation function. It's RFC 5869 for the people who want to understand more. I added this quick screenshot of that specific RFC. It is the construction. It is the function used to derive more keys from the exchange session key. Then for SSH v2, what they do is much more simple. They simply use the hash function. So you can see here that they used the derived key K, added with H, added with a label here, and with the ID there. So they just hash the derived key from AKA to get all these other encryption keys. The important part here is just to note that one shared key is very often not enough. Somehow we need to be able to derive more keys from our shared secret so that we can facilitate all these other keys, read and write keys for encryption or for MAC. So then we are at phase 3, the final phase, if you will, which is how are we now going to protect the data being exchanged over this channel. So I'll use two examples here. This is a mode of operation for symmetric cryptography. So the first one is called CTR, and I assume that most of you know what CTR is. We're going to have our encryption function E here. You can just assume AES for that. So imagine here we have this IV initialization vector, which is just a value which will be encrypted under our key K, which we're going to XOR with our message M0, and we're going to get ciphertext C0. So if you have a long message, you can split it up into different blocks, and you can encrypt it like this. Again, you have this IV, which will be encrypted, just a counter, if you will be encrypted. It will be XORed with message M0 to derive our ciphertext, C0. For the next block, if you will, typically if you're using AES, that's 16 bytes. So our message split up in 16 bytes will be encrypted using this. So the message 16 bytes XORed with the encryption of IV will get C0, C1, C2, all the way to CT. So CDR uses this block cipher for example, ESE here, to build a stream cipher. This IV here is typically chosen at random by the party who is sending the data across. And the same process is used to decrypt this. This XOR here can be used again to decrypt the same message. So it's the same construction, if you will, or the same mode of operation can be used to encrypt and to decrypt. That's one of the more famous ways, or one of the more famous modes of operation. So another famous mode of operation is called CBC, cipher block chaining. So let's go over this together on how this looks. So we're going again to have our messages here, M0, M1, M2, all the way to MT. These will have a size of 16 bytes, 128 bits. And they will be XORed with, again, this IV. They will be encrypted using, for example, AES. And they will then get C1. And then you can see that this encryption of E here will be fed into the XOR for the second block, for M1. So every block encrypted will depend on all previous blocks. As you can see here, for example, C2 will depend on the encryption of M1, so ciphertext C1, and M1 will depend on C0. So this is a nice system to get a randomized encryption. The nice thing about this thing is that plaintext, which are the same, will encrypt to different values. Why is this the case? Because this IV is a random value chosen by one of the two entities. So a randomized IV will result in different ciphertext messages when the same message is being encrypted twice. So that is how CBC looks. Now, obviously, this way of working has a problem because CBC and CTR do not provide message authentication. As you can see, we just encrypt the blocks that we received, and there is no notion of authentication. Right? What does that mean is that if we again think about Alice, Bob, and Eve, Eve is able to modify the encrypted message. And Bob, the person receiving it, will not be able to detect modifications. What does that mean? If we have ciphertext CI, we can apply this function F to it, which will just make some basic modifications to the message to get CI noted here, which we can decrypt the ciphertext and to get back our modified plaintext. So this function here, D, is not able to distinguish between a valid ciphertext or invalid ciphertext, as in ciphertext which has been modified. So for example, this is a small example here. We have CBC, so we have our cipher text block E-1, for example. We will modify the last few bits of this specific block, for example. We will decrypt it, which will then XOR with the block CI-2 to get back PI-1. And flipping bit here obviously will corrupt decryption of this block here. But you can see by the way that CBC works, this will lead to controlled changes in block PY. So if we have the next block, CI, for example, it will be decrypted and XORed with the previous ciphertext block, which we made some modifications in. This will lead to controlled changes in decryption of a specific block. Meaning that CBC does not provide authentication of your ciphertext. You can make changes, and those changes will propagate to the decryption of block UI. That's an issue. So how can we solve for that? Like how can we somehow add authentication to that? So we're going to use a MAC. A MAC stands for Message Authentication Code, and you can see this is how it looks. So we have this I here, which will consist of two functions, S and V. S will take a key as input, it will take a message as input, and it will output a tag from the tag space. We will have our function V here, which will take, again, as input a key from the key space, a message from the message space, and a tag from the tag space. And it will output or 1, meaning true, or this error term. So now Bob is able to, quote-unquote, sign this message. It's not really a signature, it's just an authentication tag. Using key K, which will be derived from the key exchange, one of the keys derived from the key exchange. As input its message, it will transfer the message to Alice, and Alice is now, because she has the same key K, able to verify this tag using the function V. So she will take the key K, M, and the tag being transferred to Alice, and able to see, okay, have this message been changed, yes or no. So very often in typical applications, a HMAC is used to build such a construction or a system, if you will. Now, this is a principle stated by Moxie Marlinspike, I believe the person who invented Signal, or one of the developers, which says that if you have to perform any type of cryptographic operation on the ciphertext before you verify it or validate the MAC, it will lead to doom. Meaning that if you send a message encrypted from one side to the other side, and if you do not check the MAC first, or the authentication or the authenticity of the ciphertext, if you don't do that, independent of any other action you can take after decryption, it will fail. So you have to always verify the ciphertext before you perform any other action. If you don't, things might go wrong, and things have gone wrong. So in order to solve for this, we came up with something which is called AE, which stands for Authenticate Encryption. So AE is a conceptual goal where we try to accomplish message authentication and data confidentiality in one single construction or one single function. So if we have this decryption of a ciphertext CI, it will give you back or the plain text or the specific error term, meaning that the ciphertext was invalid. And we have constructions, systems, which allow for that. They are called GCM, OCB, CCM, which are real-world constructions. They're out there, you can use them, which will provide message authentication and data confidentiality in one single construction. Now we have an extension on that. People have used it and seen, okay, it would be handy if you can somehow add this notion of additional data. As in, we're going to do just the same as, we're going to do the same as AE, but we can include data which is not encrypted. So we're using our AE we will encrypt everything, and everything is also authenticated. What we have now is we have our data, which will be encrypted, but not all data. We'll have a small subsection of the data provided, which will also add, which will only be authenticated, which we call AD, additional data. If it's not encrypted, it's only authenticated, which is denoted by this. We have this AD additional data. So encryption of AD and the message will give you back CI, the ciphertext, and the decryption will give you back AD, the data, additional data, and CI, which will give you back MI, the original message, or an error term if there was an issue with the authentication of CI or ID. Okay. So now, in the time remaining, which is 10 minutes, I would like to quickly discuss with you two real-world examples of a secure channel implementation. So again, just to repeat what the developer would like to have, it would like to have a secure drop-in replacement for TCP. We have TCP works great, but it would be nice if you would have a secure version of TCP. So this is what the developer wants. So we will discuss quickly two available protocols. The first one will be TLS, which I assume that most of you know, transport layer security, used with HTTPS. So TLS itself is out of two different protocols. So the first will be the TLS handshake protocol, which will basically be the key exchange, which will provide us with the keys used with the channel keys. That's one protocol. And the second protocol will be the TLS record protocol, which will provide us with AEAD capabilities, meaning that it will encrypt data provided from the application layer. So let's quickly look at the TLS 1.3 record protocol, which is the protocol implementing this notion of a secure channel. So the record protocol, all messages in TLS 1.3 are protected using an AEAD scheme, meaning, for example, the use of GCM. So we no longer require a specific MAC function or MAC construction. Why? Again, because we're using this AEAD system, and we get both confidentiality and data authentication in one single step. Again, AEAD will provide for this the additional data, but in the context of TLS 1.3, the additional data will always be 0. They'll just provide everything from the application layer to the secure channel layer, and there is no additional data. Now, the records, they will allow for multiplexing of higher level protocols. In the context of TLS, this means that you will have a handshake protocol, which is just key exchanges, if you will, application data which will be encrypted, and alerts, as in when something goes wrong on the record layer, those alerts will be able to communicate it to the high level protocol. And again, keys to support all of these features and all these algorithms will be supplied by this HKDF function, which will get these keys from the initial key exchange in the handshake protocol. That is how, from a higher level, how TLS does things. So SSH v2, how does that specific application construct a secure channel? So SSH v2 is kind of interesting, because SSH is a multi-layered architecture, as in there is not just like TLS, a handshake protocol and a record protocol. They use a wide variety of protocols. Wide variety, they use 3. So we have the transport layer, if you will, which will perform the initial connection, as in the handshake, and it will be also responsible for creating this secure channel, as in data confidentiality, integrity, and authentication, authenticity. In order to do that, they will use the binary packet protocol used to create this channel. We then have SSH authentication protocol, which will run on top of this transport layer to authenticate the client. And then we have this connection protocol, which will allow for concurrent connections over a single transport layer. So we have this transport layer, we have this binary packet protocol, and then we have this connection protocol. So let's now have a closer look at the binary packet protocol. So this is how the format looks. So what we have is we have a sequence number, a number of the data, a number of the message that is exchanged from client to server. We have a sequence field. We have a length field, as in the length of the plaintext data. We have a padding length. If you remember, we're using, in the context of symmetric cryptography, we need to use a mode of operation. Typically, every single block has a certain length. So we need to make sure that the length of our message is a multiple of block length. So we need to add padding. How much padding is defined by this field here. Then the payload, and then the padding itself. So as you can see by blue, this is encrypted to get to the ciphertext. And in the green, we have the MAC. Important here to note is that the MAC is done on the plain text, not on the ciphertext. So the MAC is on the plain text, and then we derive the ciphertext. Meaning that in order to verify, we first need to decrypt before we can verify. And then we can typically use CBC, which is using chained IV, meaning that if we encrypt two messages, the IV used for the second message is the last block of ciphertext of the previous message. So let's look at that. We have our IV here for CBC. Our first plain text block, as you can see here, that will be the length and the padding. So the first 4 bytes will be the length. The next byte will be the amount of padding. It will be the first block. And then if you use CBC, it will look like this. And then the next block will just be payload data. So that is how plain text is being encrypted using CBC for SSH. So let's now quickly dive into an attack for SSH CBC, a plain text recovery attack. So let's first look at how does the SSH server knows, or how can it perform decryption. So you have a ciphertext. From here you know that the first few bytes are the length. So with a ciphertext here, first 4 bytes are the length. So SSH server, a previous version, will first decrypt the first block. From that, it will get the first 32 bytes, as in the length. That information is then used to know how many other blocks should be read. And then when the whole ciphertext has been read, we can perform the decryption, and then we have back the plain text, and then we can verify the MAC. Because if you remember, the MAC was computed on the plain text and on the ciphertext. Now, let's try now to construct an attack, if you will, in the time remaining. What we are going to do is we're going to send the first block of ciphertext to the server. It will decrypt that to get back the length field. And what we're going to do next is we are going to send blocks of 16 bytes, 128 bits. One block, another block, another block, another block, until enough blocks have been fed to get back to this length field. We go to the next slide. This will be a bit more clear. So again, we have our ciphertext blocks here. We will take the first block, we will get the length field, we will submit IV and C1, and then we just keep submitting these random blocks, random, until we receive a MAC error. What does this mean if we receive this MAC error? That means that we have sent enough ciphertext for the SSH server to say, okay, I've now received enough data according to this length field. I will now perform decryption and verify the MAC. Now, because we've sent these random blocks here, obviously the MAC verification will fail. But what we know now, because this MAC check has failed, we know the value of the first 4 bytes. Because if we have submitted in random blocks, every block is 16 bytes, 128 bits, n times 16 is the amount of bytes. So now we know the first 4 bytes, and we can use this using a bit of algebra and CBC, apologies, a bit of algebra, we can use this to derive the first 4 bytes of any CBC encrypted block. Right? So what we will have here is we have our CI and our IV. The CI is just any block that we choose. SSH using CBC will calculate this P01, where the first 4 bytes are the length, right? Okay, and then we can know that because by submitting our blocks, we know the length of that. How can we use that to read any arbitrary data? Well, using this small formula, we are able to say, okay, for the plaintext PY, we can use this formula to derive back to get any to get the plaintext of any 4 bytes of any block using used in SSH with CBC. That's the plaintext recovery attack. It hasn't been invented by me. It has been invented by people from Royal Holloway. If you want to have more information, I suggest that you read the paper here. So with that, I would like to conclude. So what have we seen? We looked at we looked at the definition and the properties of a secure channel. We have discussed the notions of security for those properties. We looked at the different phases of our secure channel, and we looked at TLS 1.3 and SSH to better understand how to build and construct such a secure channel. So with that, I would like to finish, and thank you very much for your attention. And if you have any questions, then please ask me. Thank you.